We're going to talk about balancing equations today. We're going to work on this worksheet. We're going to be working back and forth. So I'm going to show you the color coding method. If you want to learn the T method, you can go onto my YouTube and look up the T method. I don't necessarily teach it anymore because it is not nearly as widespread. People more widely use the color-coded method than the T method. If neither method works for you, you can go ahead and look up different methods online. There's about 6 or 7 or 8 different ways of balancing equations. The most common way I teach is the color-coded method because it's the one that relates to the most majority of students. So when you're looking at these are skeleton equations. Skeleton equations are those lovely equations that have no coefficients, just balanced compounds. So the first step in your method is to write down your equation. So we're going to start with the first equation. NaNO3 add forms Na2O. Please remember that this is skeleton. And the idea in balancing equations is that everything, all the compounds are balanced on each side. There are some rules. You may not balance one part of the equation without the other. You have to balance the whole thing using coefficients. That's the number out front. You never add a subscript. You never change the compound. You balance using coefficients. Those are the numbers out front. So if you have 1, 2, 3, 4 compounds, you can only have 4 numbers that you add. Numbers out front. And for our purposes, they can only be whole numbers. Now, if you're going into not honors, if you're going to AP and some of those other higher level chems, sometimes those rules flex a little bit. But for us, whole numbers make our lives easy. So the first thing I do when I'm looking at the color-coded method is that I color code everything. So I have sodium over here and I have sodium over here. So I just underline it with the colors so that I know exactly what we're doing. Now I have an NO3 over here, and remember, NO3 is nitrate. Nitrate's a polyatomic, and if you have a polyatomic that's on each side, like NO3 retains its NO3-ness, the same identity on both sides, you can go ahead and balance it as 1. So I underline NO3 and NO3, and I can balance it as 1 compound. Then I have lead, which is Pb. I kind of underline it here, and I do Pb there. And then I go ahead and I have oxygen, which is O. So you can underline O here and there. Once you color code, you build one of each, because right now, as written, you have 1 of each. And that means right now you have 1 mole of each, because remember, 1 compound equals 1 mole. So we have 1 Na over here, and for every sodium, we have a side of nitrate. They go together. You can't build one without the other. For lead oxide, for every 1 lead, it comes with a side of oxygen. Then we can have here for every 1 lead, it comes with 2 nitrates. And over here for every 2 sodiums, it comes with a side of oxygen. Okay, so when we're looking at balancing, we always try to balance each side. So there's no subscripts over here, so it's 1-to-1 ratio, so that's really easy to balance. So then we look over here. Over here we have 2 nitrates or 2 oxygens. It doesn't matter where you start. We just have to add something else to make it match. So it doesn't matter if you do with nitrate or oxygen. We're going to add 1 more of each. So we have 2 nitrates. We have to add 1 more here because we have 1. So we need to add 1 more to make a total of 2. And for every 1 nitrate, you add 1 oxygen. So now you have 2 nitrates, you've got 2 nitrates, you have 2 oxygens, you have 2 oxygens, you have 2 sodiums, 1 oxygen, and 1 lead. Everybody is happy, so now you are balanced. Your amount of moles you've built here becomes your coefficient. So you can take your skeleton and write your coefficient out front. So we have 1, 2 is my coefficient for NaNO3, so I can put a 2 there. For Pb, I've already have 1, I've written it once. You don't write 1 as a coefficient, so you leave it alone. PbNO3, you have 1, you leave it alone. Na2O, you leave it alone. So your final answer would be 2, and then 1, 1, 1, which is just no coefficients. Okay, let's try another example. We're going to start with silver iodide, and we start by writing our skeleton equation, and we're adding it to iron 3 carbonate. Now we have iron iodide, iron 3 iodide, plus silver carbonate. Now remember, the first thing we do is I always color code everything, and then I build one of each compound. So I'm going to do red for silver. And you can do the compounds or at different times. I like to draw my elements while I'm color coding. That just is how my brain works. Your brain may work differently, and that's okay. It's up to you how you want to approach the process. Now remember, we're back to carbonate. Remember, it's a polyatomic, so it's a CO3 is carbonate, but see the parentheses in the 3 after it, that 3 means 3 carbonates. So 1, 2, 3, and then we have 1 over here. Now, there's a trick when we're looking at some of these more complex numbers. I am not saying that you're never going to need more than 1 of everything. Sometimes you do. But for the sake of simplicity, the compound with the most subscripts, like Fe2CO3, you've got dual subscripts there, you should attempt to leave it alone. You should balance that last. As a last resort, add 1 more. Because adding 1 more of these is doubling all of these. It's doubling your stuff, and that's going to make it a lot more complicated to solve. So sometimes you'll need more than 1 of the complicated one. But as a last resort, the one with dual or more than the most subscripts should be balanced last. Try to leave it alone. And also, the singletons, like silver iodine, where it's a 1-to-1 ratio, you do that one last because it's 1-to-1. It's the easiest one to figure out. So this one should be last resort. You do this one last. So you kind of do the ones that it's a 1 to like a subscript first. It makes your life easier. So it doesn't really matter where you start. You just have to start somewhere. And I always start balancing out my most complicated one first, because you really don't want any more of those. You want to leave it alone. So this is where I start. So I have 2 irons over here. I have 1 iron over here. So I'm going to add a second iron. By adding that second iron, I have 3 more iodines. Now, a lot of people are going to go, but I should go balance the iodine. Ah, but it's your singleton. You leave your singleton alone. You do your singleton last. You keep balancing the stuff on your most complicated one first. So now I have 2 iron. Now I need 3 carbonates because I have 1, 2, 3 over here, but I only have 1 over here, so I need to make 2 more. So I just go ahead and I always draw out what I'm balancing first so that I can make sure that I have enough of the one that I am balancing. So I'm balancing out carbonates. I needed 3 total. I have 1, 2, 3 total drawn. Now I have to remember to go back through and draw in my silver, because for every one carbonate, you get 2 silvers. Now I can look at my more complicated one. I have 1, 2 irons, 1, 2 irons, iron is happy. 1, 2, 3 carbonates, 1, 2, 3 carbonates, carbonate is happy. Now I can look to see if I can balance out silver iodine with what's over here. I have 1, 2, 3, 4, 5, 6 iodine, and I have 1, 2, 3, 4, 5, 6 silver. I can actually balance it out as is. I need 5 more of these because I have 6 over here, I have 1 over here. 1 plus 5 equals 6. 1, 2, 3, 1, 2, 3, 4, 5. My brain, that's why you always count. So now I can do my count. I have 1, 2, 3, 4, 5, 6 silver. I have 2, 4, 6 silver. I have 1, 2, 3, 4, 5, 6 iodine. I have 3, 6 iodine. 1, 2 iron, 1, 2 iron. 1, 2, 3 carbonate, 1, 2, 3 carbonate. I am balanced. So remember, the total number here becomes your coefficient. So I have 1, 2, 3, 4, 5, 6 as my coefficient. I have 1 iron, 3 carbonate. I've written it 1 time. I don't need to have 1 as a coefficient. I have 1, 2 of these and 3 of those, and that is my balanced compound. So I can go back to my sheet and I can go 6, 1, 2, 3 as my final answer. Okay, let's do one that's a little trickier, because you have to remember that sometimes, like in this combustion reaction, there's going to be 2 oxygens, and you got to remember they do the 2 as a whole, and on this side you have 2 oxygens. You got to do the whole side, not always by element. So let's remember, the first thing we do is color code. So I'm going to do my carbon first. I've got 2 carbon, and I have 1 carbon over here. For every carbon here, I have 4 hydrogen. And over here I have 2 hydrogen. So then we have oxygen, and I have, in this compound, I have 2 oxygen. And then here I have the diatomic oxygen that's coming in pairs. And then over here I have 2 oxygen. And here I have 1 oxygen. So this oxygen, you have to remember, you got to take it as a whole. Like, you can't balance this oxygen separately than this oxygen. It's an oxygen total for this side and an oxygen total for this side. Now, the good thing though is you got this diatomic oxygen here. So we're going to try to balance everything first before the oxygen. Remember, as always, we try to leave the element with the most subscripts alone, because it starts like exponentially getting bigger for everything. So it doesn't matter where you start, except we're going to do the oxygen last because of this diatomic oxygen. So let's start with carbon. We have 2 carbon over here. We have 1 carbon over here, so we have to add another carbon. Because 1 plus 1 equals 2, we need 2 total over here. And then we need, for every 1 carbon, we have 2 oxygen, so we have to add 2 oxygen. Now everyone's going to be jumping in to do the oxygen, but right now we have 1, 2, 3, 4, 5 over here. There's no way of doing an uneven number, so we have to get oxygen as a whole number. So the easy way of doing that is balancing the hydrogen. So we have 1, 2, 3, 4 hydrogen over here, and over here hydrogen comes in pairs. So we need to add 1 more pair to make 4 total hydrogen. Now that I have 4 total hydrogen, remember each hydrogen comes with a pair of oxygen. An easy mistake is to forget to add your next item. Then you can go ahead and count. Over here we have 1, 2, 3, 4, 5, 6 oxygen. Over here we have 1, 2, 3, 4. Now, you can do it in, there's a lot of ways of approaching it. A nice easy way that works for my brain is that there's 2 oxygen on here, and this has 2 oxygen, so I just cover them up. So that I can look at the rest. So the rest is 1, 2, 3, 4 oxygen. I have oxygen that comes in pairs here, so I need to add one more pair because this needs 4 oxygen. And then I can do my count. I have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 4 hydrogen, 2 carbon. Everything is happy. Then you write your subscripts, or sorry, my coefficients. I have one of these to one of these. I don't need to write a coefficient. I have 2 here, so I put 2 out front. I have 2 here, so I put 2 out front. And I have 2 here, so I put 2 out front. And if you're keeping track on your sheet, it is 2, 2, 2. Now we're going to look at the next one, which is zinc sulfate, lithium carbonate, zinc carbonate, and lithium sulfate. Now, you can write it down, or some of these you can kind of visualize. If you look at it, I have 1 zinc over here. There's no, zinc and sulfate have no subscripts that are unusual. I can look over here that zinc and sulfate have no subscripts that are unusual. They are the exact same. I have Li2, I have Li2. That's the exact same, and carbonate hasn't changed. They just changed places, but they didn't change amounts. This one is already balanced. So you can just put a check mark by it. It's already balanced, and you can kind of check that out. Another thing that you can do is sometimes see patterns, okay? So we have V2O5, and we have calcium sulfate. Well, calcium sulfate, then we have calcium oxide. These two are a 1-to-1 ratio, which means it's easy to balance. Then we have V2S5. If you look here, these vanadiums. The vanadiums are the same already. All we need to do is flip or balance the S and the O. So S5, I could put a 5 here. O5, I can put a 5 here. And it balances because the calcium is the same in the 1-to-1 ratios. Let's look at number 6 again, or for the first time, but me recording it for the first time. Number 6 is one of those ones that if you were writing it down, and a lot of times I tell my students, when in doubt, write it down and see how, if you're going down after something. That's like my trick to doing it. Like if I'm going down or not going down after things, it kind of is it's like a physical reminder of whether there's a subscript or not. But we can look at it. Manganese doesn't have a subscript. Manganese doesn't have a subscript. It's already balanced as 1-to-1. Nitrate, that's NO2, has a subscript of 2. Nitrate over here has a subscript of 2. It's already balanced. Beryllium has no subscript. It's written 1 time. Beryllium has no subscript. It's written 1 time. It's a 1-to-1 ratio. It's already balanced. Chlorine has a subscript of 2. Chlorine has a subscript of 2. It's already balanced. So this one is a 1-to-1-to-1-to-1 ratio. It's just one of everything. Now, I want you to try number 7 on your own and see if you can think through your answer. Number 7 is one of those ones where you could draw it out, but you could also kind of figure it out just doing some mental calculations. So look, silver bromine, it's a 1-to-1 ratio. So that's one that I always will do last. So look, gallium to gallium, it's the same. 1 Ga, 1 Ga. PO4 to PO4, it's the same. 1 PO4, 1 PO4. Now I look, I have 3 silvers here and 3 bromines here. If those subscripts were different, I'd have to draw it out and do math. But because those subscripts are the same, the 3 silver to 3 bromine, and it's a 1-to-1 ratio here, I can just put a 3 out front and be balanced. Okay, there are sums that you just cannot do in your head, and it's really important to remember that hydroxide, this OH here, is the most common polyatomic to split. And once it's split, OH becomes H2O, you have to treat them as two separate elements and no longer as one polyatomic. So this is an important one that we're going to do together because it involves a lot of moving parts. So you have 2 hydrogen here. You have 3 hydrogen here because it's 3 distribute. So you got 3 hydrogen. You have no hydrogen in here and you have 2 hydrogen over here. Then you can do your SO4. The cool thing about this SO4 is that there's an SO4 over here and an SO4 over here. So you can treat the SO4 as one item, so it's one polyatomic. Then you have boron. So you have 1 boron here, and you have 2 boron here. Then you have oxygen. In this one, this 3 distributes, you have 3 oxygen. And over here, you have 1 oxygen. As always, it's really important to remember you don't want to add more of the item that has lots of subscripts. So this B2SO43, we're going to try to stay away from. Going to leave it alone. If when in doubt, leave the one with all the subscripts alone, because if you add extras of these, you're doubling your beryllium, you're tripling your sulfate. So leave it alone. Then you're going to look at the other ones. Over here we have 3 hydrogen, 3 oxygen. It's an odd number. You really can't have half of a coefficient. So when at all possible, make your odd numbers even numbers because it makes it easier for coefficients. So can I easily make this into a whole number? I can, because I have 1 boron over here, but I have 2 over here. I can double it. When you double an odd number, you get an even number. So I'm going to go ahead and I'm going to do 1 more boron. And for each boron, it comes with 3 hydrogen and 3 oxygen. Now, everyone generally once you get those all even, they always jump over to this H2O. But that's the last thing you want to balance because you still have 3 SO4s. And that SO4 is attached to the hydrogen, so it's not going to be able to be balanced. You'll be going back and forth a lot. So now we're going to balance our SO4. So we're going to add 2 more over here because you need 3 total. Once you have 2 added, you're going to go ahead and remember your hydrogen. Now I have 2, 4, 6, 12 hydrogen, and I have 6 oxygen. Now, each hydrogen comes in a pair, so I need 5 more pairs to make 12. One, 2, 3, 4, 5, 6. Mrs. McGuire still needs to count out loud sometimes. And each pair comes with a side of oxygen. So I'm going to put in my side of oxygen. Now I have 1, 2, 3, 4, 5, 6 oxygen. 1, 2, 3, 4, 5, 6 oxygen. 3 sulfates, 3 sulfates, 2 borons, 2 borons. 3, 6, 8, 10, 12 hydrogen. 2, 4, 6, 8, 10, 12 hydrogen. I am balanced, so I'm going to go ahead and write my coefficients. 1, 2, 3 is my coefficient here. 1, 2 is my coefficient here. I've written this one time, so I've written this one time. I don't need to write 1 as my coefficient because I've already written the compound one time. And remember, when you write compound one time, that's 1 of the coefficient. And I have 1, 2, 3, 4, 5, 6 here. That is my coefficient. And then I can go back to my sheet of paper and write 3, 2, 1, 6. Now, we're going to talk about the next one because This again looks really tricky with the 8 and the 2, but it's a very easy one to do in your head because of the O2 here, and you have an O2 here, so the O2 is a 1-to-1 ratio. So I have 8 S's, so I need 8 S's, so I put 8 out front, because 1 times 8 is 8, and 8 times 1 is 8. I have 8 O2s, so I put that 8 out front here, and I have 8 O2s, and that is how I balance that. Let's do our last practice, and I think this is one that you could either draw out, or you could think yourself through without drawing if you're looking at ratios. If you look over here, I have 1 iron here, I have 1 iron here. It's a 1-to-1 ratio, it's balanced. I have 1 silver, I have 1 silver, it's balanced. I have 2 nitrates and 1 nitrate. Well, because this silver is by itself, I can put a 2 out front here. Now I have 2 nitrates, but 2 silvers, but there's nothing preventing me from putting a 2 here, because when it's by itself, I can do to one to the other without really having to worry about balancing everything out, because it doesn't affect anything else. And that is how you balance chemical reactions.